Welcome everybody to the next Georgia Tech Graph Theory seminar. Our speaker today is Xiaonan Liu from Georgia Tech, our very own, and she will tell us about the number of Hamiltonian cycles and planar triangulations.
Okay, thanks for the introduction. Thanks for coming. I'm going to talk about the number of Hamiltonian cycles in planar triangulations. So this is a joint work with Professor Xiaonan Liu. So today I'm going to talk about number of Hamiltonian cycles in four connected triangulations. So let's first look at some early results. So in 1931, Whitney showed that free-fall connected triangulation contains a Hamiltonian cycle. So, and Tutt extended this result to all four connected planar graphs in 1956. That is, every four connected planar graph contains a Hamiltonian cycle. So this result is very good. So now one natural question comes. So what can we say about the number of Hamiltonian cycles in four connected planar triangulations or in four connected planar graphs? Okay, so let's first look at some results about this question. Oh, sorry. Let's first look at one kind of graph, the double wheel graph. Okay. So the double wheel graph with n vertices is that first we have a cycle of length n minus 2. And inside this cycle, we have one vertex here. And maybe we can call it U. And outside, we also have one vertex V. So, and you have the degree of U and V is n minus 2. It's just, sorry about that. We join these two vertices to all n minus 2 vertices in the cycle. Here, this graph is W6, but we can have more vertices in the cycle. So what can we say about the number of Hamiltonian cycles in Wn? So let's count together. Yeah, it's not obvious, but it's easy to, I think it's easy to count it. So first, we know that for each Hamiltonian cycle, there are two edges incident with each vertex. So for U and V, so maybe we can say, so if for the two edges, so in each Hamiltonian cycle, the two edges incident with U is this. So the two edges are contained in one triangle. So what can we say about U? So actually, in this Hamiltonian, if we want to get a Hamiltonian cycle, so the two edges incident with U should be also contained in one triangle. Okay, so here I can give you an example, like if we choose this one. Okay, so yeah. So this is a Hamiltonian cycle. So we use these two edges are also contained in one triangle here. Okay. So for this kind of two edges, we have n minus 2 choices because this cycle have n minus the length of this cycle is n minus 2. So we have n minus 2 choices of such pair. And also for U, we have n minus 3 because we cannot choose these two edges. Because if we choose these two edges, we cannot get a Hamiltonian cycle. So this is the first this is the first type of Hamiltonian cycles in Wn. So then the second is that the second class is that we choose so it's the double wheel. So this is V, this is U, they are all edges. So So now if we choose two edges incident with V, which are not contained in one triangle like this. Okay, so what can we say? The two edges about the two edges incident with U in a Hamiltonian cycle. Actually, for this case, we can only have two because it's like we can in this direction. So we can only do this. Or another direction, like, let me use this one. So this is another direction. So we can only have two. So for this, if the two edges incident with V are not contained in triangles, actually can only have n choose n minus 2 choose 2 minus n minus 2 choices, and means the two directions. So this is the total number of the Hamiltonian cycles in Wn. Okay, so after calculation, this one is n minus 2 times n minus 3 plus n minus 2 times n minus 4. So actually, this is just 2 times n minus 2. Sorry, that then. Let me think about this one. Maybe there is a, is it correct? N minus 2, n minus, oh. Oh, sorry, this should be 5, not 4. Then we get it should be 2 times n minus 2, n minus 4. Okay. Yeah, so this is, so now we calculate this one. So, and also we have one conjecture about the number Hamiltonian cycles in 4 connected triangulations. So in 1979, Hakimi, Schmeichel, and Thomson conjectured that if G is a 4-connected planar triangulation with n vertices, then G has at least 2 times n minus 2 times n minus 4 Hamiltonian cycles with equality if and only if G is a double wheel. So this is the number of Hamiltonian cycles in Wn. So actually we can say that in Wn, we know that we have n minus 2 vertices of degree 4 in this cycle. So actually in our proof, we can show that, and we can know that if we have too many vertices of degree 4, it's very hard for us to find many Hamiltonian cycles. So I think it's the evidence to support this conjecture. Okay, so let's look at some previous work about this conjecture. So also in 1979, in the same paper, they proved that every 4 connected n-vertex planar triangulation has n over log 2n Hamiltonian cycles. And in 1999, Beim, Herent, and Tuck showed that every 5 connected planar triangulation G has at least 2 to omega n to a quarter Hamiltonian cycles. Okay, so then we can say that for 5 connected planar triangulation, actually we can have an exponential bound. So it has a lot of Hamiltonian cycles. And so also in so recently, Brakeman, Sophia, and Van proved that every 4 connected n-vertex planar graph has at least 12 times n minus 2 over 5 Hamiltonian cycle. Actually, this is a linear bound. So yeah, it's good, but because in the conjecture, we have a quadratic bound. So yeah, we still have a lot of work to do. So now for the for very recent results. So in Alahmadi, Aldred, and Thomassen show that every 5 connected planar triangulation G has at least 2 omega n Hamiltonian cycles. So actually for this one actually improves the work here. So, and also the idea in this paper is very useful in our work. And also in 2020, Liu showed that every 4 connected n-vertex planar triangulation with big O log n separating 4 cycles has omega n over log n squared Hamiltonian cycles. So here, this is some 4 connected planar triangulation. Here is with fewer separating 4 cycles. Actually, it's also it's just this 4. It is 4 connected graph, but it's very close to 5 connected. But I'm not sure how to say it. Maybe it's a relation of 5 connected graph like that. So our work is to actually improve Liu's work. And so the first result is that, let me show, that we showed that if G is a 4 connected planar triangulation with n vertices and big O n over log 2n separating 4 cycles, then G has omega n squared Hamiltonian cycles. Okay, so so this theorem improves Liu's work. So this bound and this bound. Also here, sorry, I want to say that a separating 4 cycle is that first it's a cycle of length 4, and if we delete this cycle from this graph will be disconnected. So then this 4 cycle is called separating 4 cycle. So, and also we have a result about the graph with minimum degree 5 is that let G be a 4 connected planar triangulation with n vertices and minimum degree 5, then G has 2 to omega n2 quarter Hamiltonian cycles. So yeah, so also this result improves the result in 1999. So we just change the condition of this one to 4 connected and with minimum degree 5. So okay, so from here we know that we need to deal with a lot of separating 4 cycles for this case. Okay, so this is our recent result, our result. So now let me show our idea. So first, yeah, this is a useful idea. So, and this idea comes from the paper, the paper of Alahmadi and Aldred and Thomson. Yeah, that idea comes from this essay. So first, we find an independent set S such that each vertex in S has degree at most 6. And if F is an edge set, is obtained by choosing exactly one edge from each vertex V in S, then G minus F is 4 connected. So if G minus F is 4 connected, we know that we can apply Tutt's theorem to G minus F. We know it has a Hamiltonian cycle in G minus F. So here is like, if we can find such independent set, we can find at least 3/2 to the size of S Hamiltonian cycles in G. So we can get an exponential bound by this. So I can say it here. It's like, so if we can find such set S, it's like we can double count this set F C. So this F is just an edge set. We take exactly one edge from each vertex V in S. And this C is just we choose one Hamiltonian cycle in G minus F because we know there exists. So now we know that each vertex in S has degree at most 6. So we know that since G is 4 connected, so it has minimum degree 4. So all vertices in S have degree 4, 5, or 6. Okay, so now if we denote, there are A4 vertices of degree 4, and A5 vertices of degree 5, and A6 vertices of degree 6. Okay, so now first for F, so how many choices can we of F? So it's like, so for each vertex, we can choose one edge. So actually the number of F is 4 to A4 plus 5 to A5 times 6 to A6. This is all choices about F. Okay, so now if we took a set like C is the collection of all Hamiltonian cycles here. And we know that for each Hamiltonian cycle C, it's how many, it's like at most, how many F can we choose the same Hamiltonian cycle? But here we can only choose, so it's like for this F, if we have a Hamiltonian cycle C, at most 2 to A4 times 3 to A5 times 4 to A6, because the Hamiltonian cycle used 2 edges incident with the with each vertex. So, but the remaining edges we can still pick, like, so we have at most like this. So then we know that, say this one, so for the number of F is less than C times at most 2 A4, 3 A4, 4 to A6. Okay, so now we know that, oh, the Hamiltonian cycle C is greater than 2 A4 times 5 over 3 A5 and 6 over 4, 3 over 2 A6 to A6. So now this one, this is just S. So we get this bound. So now it's very important for us to find such independent set. If we can do this one, then we are good. So then the next step.
May I ask a quick question? So if you just want a lower bound that is exponential in the size of S, then the number 6 is not, if you go get each vertex to be of degree at most 100, where 100 is a constant, you would still get an exponential lower bound, right?
Yeah, yes. We can just improve this one. Yeah, it can be, actually we can improve this degree, but if the degree is very small, it's very useful for the later proof. So we just choose a small number here.
Okay.
Yeah,
Thank
very
you.
good. That's a good question. Thank you. Yeah, so we can choose, actually this number can be improved to any number because we can still get a number larger than 1. So that's very good. So, but here we use 6 to the because it's useful for the later proof. Okay, so to find such a good independent set, so first we need to make sure what should we what should it's like if the independent set satisfy because it should satisfy some conditions, then we can do this. So here, this is we want to find the condition of the independent set S. So first, so if we just delete all edges in F, so if G minus F is not full connected, we want to say which case we want to say what will happen here. So if this is G minus F, so if it's not full connected, we will have a minimum card of size at most 3. Maybe we can let it be K, like K. So, and we will have some component G1, G2. So this is G minus F. So, but G minus K, because G is full connected, so G minus K is connected. Okay, so then we will say that there are some edges between these two components, and this edge, because it's a triangulation, so we know that these two vertices has exactly two common neighbors. It's like, and these two common neighbors must be contained in K. Yeah, if it's not like it's not a cut edge, so it's like because it. Let me see. Yeah, so it's just because these two vertices has exactly two common neighbors, and they must be contained in K. Otherwise, it cannot happen. So then we know such edge, the two vertices incident with this edge has two common neighbors and they are contained in K. So if we have only one such red edge, what do we say? So then the K should have size 3. So it's like this is the red edge, and these two vertices are contained in K. And we also, the black vertices are contained in K. Okay, so the red edge is one edge in F. So we will have like if we delete this edge and these 3 vertices, then it's not connected again. So since for each red edge, we know that one vertex of the red edge is in S. So in this case, is that a vertex in S is contained in a separating fold cycle. Or so if this, because we know like this one, actually we know this one is, so these four vertices, just the red cycle, is a separating fold cycle. So, and this vertex can be contained in S, or this vertex can be contained in S. So we have these 2 cases. So for the last 2 cases is like if we have two such red edge, and first if the common neighbor, so first we know that these common neighbors are contained in K. So here, so if we have one, rather this is E1, this is E2. So if they have the same common neighbors like this, then we will know that 2 vertices in S are contained in a fold cycle. Like this, if this is in S, then it's, if we assume this is in S, this is in S, then two vertices in S are contained in a full cycle. So if they are not contained in a full cycle, we will have such like this. So since the black vertices are contained in K, so since the K has a size at most 3, so if we have two such red edges, like then we know if we delete these two red edges and these 3 black vertices, we can, it's not connected. Actually, then we know it should have this form, and then we can know two vertices in S are contained in a 5 cycle. Like if this one. Okay, so also the last cases is that if we have 3, if we have 3 such red edges, and the common neighbor, like this one. Yeah, because we have at most 3 black vertices and we have 3 red edges here. So it will like this. So then, so to see it clearly, so here is just a 9-vertex graph called diamond 6 cycle. So here, let's look here. So this is just the diamond 6 cycle. So, and we call this 6 vertices crucial vertices because some vertex in S can be contained in it. So here we know that there are 3 vertices in S contained in this diamond 6 cycle. So we call this 6 vertices crucial vertices because they may contain some vertices in S. Okay, so also same, we also define diamond 4 cycle here because, so actually it's same as the first graph here because these two vertices can contains 1 vertex in S. So these 2 are called crucial vertices. But this is used in our proof, but I'm not sure I will cover this one here. So first, let's look at some definition is that if the independent set S saturates a full 5 cycle, say, e.g. if S contains 2 vertices in say. And the definition for if S saturates a diamond 6 cycle D, if and only if S contains exactly 3 crucial vertices of D. It's like we have 3 vertices in S, like in such location. So yeah, so now then we know that we can know the properties of this independent set. So if all vertices in S have degree at most 6, or S saturates no 4 cycle, or 5 cycle, or diamond 6 cycle, and also here no vertex in S is contained in a separating 4 cycle, and this condition can be replaced by the minimum degree 5. Okay, and the last condition is that no vertex in S is adjacent to 3 vertices of any separating 4 cycle. So if it has such properties, then it's very good because if we delete exactly 1 edge from 1 edge incident with the vertex in S, then G minus F is full connected. So we have this lemma. So this lemma states that G minus F, so S is a good independent set, and let F be an edge set of size of S edges such that
G minus F is 4 connected. Okay, and after the calculation, we know that if C is a collection of Hamiltonian cycles in G, then we know we have at least 3/2 Hamiltonian cycles here. Okay, so now our goal is to find such good independent set. So look at the condition here. So the first, actually, we know that the average degree of G is less than 6. We can find many vertices of degree at most 6. And by four-color theorem, we can find a large independent set of vertices of degree at most 6. So now our main goal is to find an independent set such that it saturates no 4, no 5, or diamond 6 cycle here. So we need to do this one. So if we want to do this one, look at these two lemmas. So also Liu showed that let G is a 4-connected planar triangulation, and S is an independent set of degree of vertices of degree at most 6, and S saturates no 4 cycle. Then we can find a subset. Also, the size is at least S over 541, such that S prime saturates no 5 cycle in G. Okay, so Alahmadi, Aldred, and Thomassen showed that if S saturates, so S is also an independent set of vertices of degree at most 6, and S saturates no 4 cycle. So we can know that there exists a subset S prime of size at least S over 301, such that S prime saturates no diamond 6 cycle. So if we have these two lemmas, we know now our goal is to find an independent set saturates no 4 cycle. Okay. So now this is the lemma. So because we want to find such a large independent set, but here we have these two structures. So if G is a 4-connected planar triangulation, so either we can find a large independent set of vertices of degree at most 6, such that it saturates no 4 cycle in G, or we can find, so if we cannot find a large independent set saturates no 4 cycle, then we can know there exists non-adjacent vertices V and X such that they have a lot of common neighbors. Okay, so actually because we are considering that the 4-connected triangulations with at most, with not many separating 4 cycles or minimum degree 5. So actually these two conditions, we can use the not too many for separating 4 cycles and the minimum degree 5 to solve it. So if we can find an independent set as saturates no 4, no 5, or diamond 6, then we are happy. So now what do we want to do is just this case, is that there exists non-adjacent vertices phi x such that they have a lot of common neighbors. So we come to this structure. So like we denote all common neighbors of V and X like U, B1, B2, like B to W here. So, and also we can know that actually in the 4-connected planar triangulation, B1 and B2 to BT are blocks. So it's a chain of blocks here. So it can be an edge or a graph of some vertices, just intuitively that so at first we thought if we have some vertices here, so it's just take B1 as an example. If we have, actually it has at least it's like if we can have some vertices, like, so here I just use this one. So we just guess that there are two Hamiltonian paths in B1 from U, between U and B1. It's like from U to B1. So if it's not an edge, it has some vertices, we guess that there are two distinct Hamiltonian paths between U and B1 in the block, capital B1. And yeah, it's just very intuitive idea, and it's true. By Thomson's result, we can show it's true. So now our idea is that if we have a lot of such, if V and X have a lot of common neighbors, we can find, like in a Hamiltonian path in U and like in U, between U and W. We don't use V and X here, but also in outside, we find if we can find a Hamiltonian path between U and V, use V between U and W, use all vertices outside this one, and also V and X. So then we know that the union of these two paths is a Hamiltonian cycle in G. Okay, so now here we just know, oh, if we, so then we can know that. So here is just, I'm not sure if I have time to say this. So here is just, we use we use the Thomson's result, Thomson theorem to show this one. Like, so G be a near triangulation is like all faces are triangles except the outer cycle. So with outer cycle UV, W, X, U. So, and assume G is not equal to C plus Vx, then one of the following holds. So either G minus Vx, either it's just one path, like this. It's just a path between U and W, or it will have at least two Hamiltonian paths between U and V in G minus Vx. So actually it's just, then it's just to show the, like our idea first in the block. If B1 is not an edge, then it has some vertices. Then we know there are there are at least two Hamiltonian paths between U and B1 in B1, in the block, capital B1. Okay, so this is to find the Hamiltonian paths between U and W. So also we proved another similar result is that, so it's U, V, W, X. So the condition of G is still the same. So G minus WX, so here is, because now we want to say the Hamiltonian path between U and V in G minus W and X. And also we show that if it's just an out-planar near triangulation, it's just all vertices inside this full cycle lies in this path. So there is no, maybe it will be like this, but yeah, it's just all vertices lies in this path, UV path. Then we can just find one Hamiltonian path between U and V. But if it's not a planar graph, out-planar graph, then we can find at least two Hamiltonian paths between U and V. So to show these two lemmas, actually we use the some theorem about third path. So yeah, in 1983, Thomson showed that if G is a two connected plane graph and C is its hot cycle. So it's like, so first let me say the definition of third path. So if we have a third path P, so the bridge of the third path P is like if we have one edge which is not contained in this path, but the two vertices incident with this edge are contained in this path. So this is called a bridge. Or we have a component here, and we have some edges incident with this path, like this. Okay, so this is a component, and it has some edges adjacent to incident with the vertices in P. So these are the bridges. So for the third path, also for these two vertices, so for all vertices that's the bridge intersect the VP are called the attachment of each bridge. So if so for third path P, so if P is a third path, it means that all bridges has at most three attachments. Yeah, so for C third path, it's like if the bridge contains one edge in C, then this bridge has at most two attachments on P. Oh, I'm not sure if I say it clearly. So so here it's just if G is a full connect, so we can use this one to here. We can show how we use Thomson's theorem to show that it's like, so because we know it will have like this, so it's a block here. So from Thomson's theorem, we know that this block is two connected plane graph, and we let this be, so say it's outer cycle, and we choose X, choose like this is U. So this is X. And this one is UVW. Choose this one be Y. So we can find, so an E in edge, and E is an edge contained in C. So we can, so this is edge here. So we can find a C third path P between X and Y. So actually this C third path is just a Hamiltonian path between U and W in G minus Vx. So yeah, also, so this is for the first lemma, it's just the UW. So for UV, we use this theorem. In Thomas and Yu shows that G be a true connected planar graph with out cycle C, and let UV be two vertices in this cycle, and EF are two edges in this cycle. So we can find a UCV third path between U and V such that EF is in EP. Okay. So we use this theorem to prove this lemma. Okay, so now this is our, so for connected planar triangulation without too many separating four cycles. So either we can find a good independent set of size, this one. So if we get this one, we know that we can find 3/2 omega and such Hamiltonian cycles. So actually this is very good, but we cannot, so actually the number of the separating, so because our theorem shows that with at most big O, n over log 2n, separating 4 cycles. Yeah, so actually, because we want to this bound be very large, but we also want to get a large independent set. So yeah, so we know that this bound is larger than the n squared. Yeah, but we cannot, because we want to improve this bound. So we must let this number be 8. Okay, so then we just do this one. If G has 2 non-adjacent vertices phi and x such that they have a lot of common numbers, so the number of these common numbers is at least 16 log 2n. So here is like, because we know that we will have at least 16 log 2n blocks here. Oh, we can use it. We can use this. So now, oh, can you see my screen now?
No, not anymore. It disappeared.
I'm sorry about that. Let me just try again. Okay. Is it back? Yeah.
Yes, we can see it now.
Oh, okay. Sorry. So here is like we have a lot of blocks here. So if these blocks have if this block, we have a lot of block like 2. If we have 2 log 2n blocks that they contain some vertices, we know there are two Hamiltonian paths between Bs minus 1 to Bs. So if we can know there are at least 2 times log 2n blocks such that there are at least 2, then we can find U2W. There are at least 2 to the 2 log 2n n squared Hamiltonian paths between U and W. Between U and W. So then we can find n squared Hamiltonian cycles in G. But if not, that means that we have a lot of blocks that is just one edge. So we can have a consecutive like blocks, they are just one edge. So this means that we have a lot of vertices of degree 4. And yeah, because it's like it will be in this one. Yeah, because we have a lot of consecutive blocks, they are just one edge. So then we can know that actually we can get a lot of consecutive vertices of degree 4. So if we get this one, so just say this one, we have the idea to contract one edge and apply induction on the vertices of the graph. Yeah, because if we contract this edge, just example, okay, so then we get to, so we contract this red edge and we apply induction, we know that since this vertex have degree 4, so each Hamiltonian path are incident. There are 2 edges incident with this vertex, this red vertex. Let me use this one. So and we can use. So let me just. So if the Hamiltonian path passes through these 2 edges, so in our graph here, we can use this to modify in this 4 cycle, and we can get the same. We can get the Hamiltonian cycle in G, if this is G star. Okay. Also, same for other cases, we can just modify here, and we can get the Hamiltonian cycle in G. So now it's like if we apply induction, we can only know that G has omega n minus 1 squared. We need to find new Hamiltonian cycles. So we just found that all cycles we obtained now uses this red edge. So we want to find if we can find some linear bonds, just like n Hamiltonian cycles doesn't pass through this red edge, then we can our statement. So here we just we think that we delete these 2 vertices, and we get this one. So here we delete. So if we delete these 2 vertices here, if then in this, and we add 1 edge here. So if we can show there are linear Hamiltonian cycle passing through these 2 edges, then because this is our previous graph, so then we can use this to modify it to get a new Hamiltonian cycle. If the Hamiltonian cycle passes through these 2 red edge, we can use the green edges to modify it and to get a Hamiltonian cycle in G. And just pay attention here, we don't use this edge. So yeah, so now this is our idea. So here, so we proved 1 lemma that we let G be a 4 connected planar triangulation with n vertices, and at most C1 n over log 2n separating 4 cycles. Then for any 2 edges EF in a triangle in G, there are at least C1 squared times n Hamiltonian cycles in G, because we want to show that in 1 triangle, there are many Hamiltonian cycles passing through 2 edges. Okay, so, and also in the proof, we need to use a result of Jackson and Yu in 20 and 2. So yeah, but I don't have time to complete it. So let me just go to the next case. So the next case is the minimum degree 5. So for the observation, if delta J equals 5, then we can know there exists at least 2 Hamiltonian paths between A and B. In this one, the overline C means the subgraph bounded by the cycle C. Okay, minus also this is VC minus AB. It's like so if delta G equals 5, so we cannot have a vertex of degree 4. So then for each four separating cycle, we can find like at least 2 Hamiltonian paths between these two vertices or these two vertices or other cases. So because if we only have one path, if we only have one Hamiltonian path, we will have some vertex of degree 4. So this is for UVW. For UV, so if we only have one Hamiltonian path, actually for this vertex, X, W, the common number of X and W should have degree 4 here. Yeah, if it's not 4, it will contradict that G is a 4 connected graph. So for this one, we know that if it's a planar graph, we will have, so this one, if it's a planar graph, we will have some vertex of degree 4 here. So if delta G equals 5, we will know there exists at least 2 Hamiltonian paths between A and B. So, okay. So look at this lemma. It's like, now if we have minimum degree delta G equals 5, then, so because now if then we can know, we cannot just in this one, in this picture, we cannot have 2 consecutive blocks just via an edge, because we will have a vertex of degree 4. So then for this, so for minimum degree 5, so we don't need to do like, we don't need to consider this case. If they have a lot of common numbers, then they are good. So now we consider the independent set. Now we can get an independent set of large size such that saturates no 4, no 5, or diamond 6 cycle. So here, it's like, first, if we may assume that it has this one, and we may assume that each vertex, we have a lot of vertices in S are adjacent to exactly 3 vertices of a separating 4 cycle in G. So if we don't have many vertices in this, we can find the good independent set. Then we are good. But now also this too means that there are a lot of separating 4 cycles in G. So, and we can observe that these 4 cycles either is just one contain the other, or they have disjoint interior like this. So for each 4 cycles, we can observe this one. So either they have disjoint interior, or they are nested like this. So if they are disjoint, like, we can contract the interior of each 4 cycle to 1 vertices, and they are still 4 connected. So if it's still 4 connected, a Hamiltonian path like this. But for each, we know that in G, there are at least 2 Hamiltonian paths between this one, like between this to this. So we can also have 2 to the bound. Yeah. So now we assume that we have a lot of 4 separating 4 cycles, and they are nested. So the details are very complicated. So it's just we construct one tree. So for this tree, and each leaf of the tree represents a Hamiltonian cycle in G, and then we analyze a lot of cases. Then we complete the proof. Oh, sorry, I think I used all time. Sorry about that. So that's all.
All right. Let's thank Xiaonan.
Thank you.
Are there any questions? Can you, Xiaonan, could you just have the slide with the definition of the tree up? I just want to read it.
Oh, this one?
No, the next one. Next one after this.
Oh, yeah.
Thank you.
Actually, for the trees, like, because now we have a lot of nested force separating force cycles. So the meaning is that if we let Hg denotes the graph obtained by from G by contracting say G minus, it's like let me just. So actually, it's very. So this is C1. So first, we contract the interior of C1 to 1 vertex, and we can find a Hamiltonian cycle in H1. So this is called H1.
Mm-hmm.
So so for each Hamiltonian cycle, we know that since this has degree 4, like if it passes through these two edges. So then we look at, because we know that C2 is nested, is in here. Like, so this is C2. So we contract the interior of C2 to 1 vertex, and to see like the Hamiltonian path between these two vertices, like this. So it's a Hamiltonian path in H2. Also, then we look at C2, and we want to find the Hamiltonian path between these two vertices. But in C2, this is C2. We know C3 is inside it. So okay. So we find the Hamiltonian path between these two vertices. And since the two edges incident is just do it to construct the to get the so the root represents a Hamiltonian cycle in H1. Then if V is a vertex of T at distance S from R, then V represents a Hamiltonian cycle in HS plus 1. Then because the last step is HT plus 1 is the graph G, so then we can know that the leaf of the leaf of this tree represents a Hamiltonian cycle. So so if we follow this step, we get this tree. So if we just do this one, if the leaves, we have a lot of leaves, then we are happy. But sometimes if we don't have enough leaves, it means that we have one path in our tree that the internal node all have degree 2. It's just like this. If it has something, we can have enough leaves, but now we cannot have enough leaves. But so for the case 2 is that we have such paths But then there are some properties of these 4 cycles. So we do another way to solve this kind of case. Yeah.
I see. Thanks.
Yeah, I'm not sure if I say it clearly.
I think I get the idea.
Oh, thank you.
Are there any more questions?
Okay, so what's next, Xiaonan? What's next? What are you going to do next?
Oh, yeah. We want to, Professor Yu and I want to extend this result to the projective plane. So now so our results, let me just, so our results now is for connected planar graphs, planar triangulation. So we want to say if we can still have the same result for the 4 connected triangulation in projective plane. So if G can be embedded in a projective plane. So we want to prove if it can still have such results.
Okay, because the existence of a Hamiltonian cycle in a 4 connected projective planar graph is known. So it makes sense to extend it to the projective plane. But for torus, it is not known. So we don't know whether 4 connected toroidal graphs have Hamiltonian cycles. So that's the reason we study projective planes.
There's a question from Zishia in the chat. What about internally 4 connected planar graphs?
Oh, so internally 4 connected planar graphs. Professor, do you have any idea about this question?
So it's not, those graphs are not exactly 4 connected, and they don't have to have Hamiltonian cycles. So the number could be 0, but presumably if you add additional conditions, you can relax this. You can relax this conditions in the result to get the certain number of Hamiltonian cycles in certain internally 4 connected graphs. But for all of them, for the whole class of internally 4 connected graphs, we can't say anything.
Yeah, but I'm not sure if this internally 4 connected planar graph, I'm not sure if we can apply Thomson's result to such graph.
We can. Well, we can, but it doesn't guarantee a Hamiltonian cycle in those graphs.
Oh, okay. Thank you.
Any other questions? If there are no more questions, then let's thank Xiaonan again. And our speaker next week will be Florian Pfender from University of Colorado, Denver.